We then utilize the capabilities of our coverage solution, GNATfuzz. So we instrument the user code at the source code level, and this will give us dynamic feedback of the statement coverage that we're achieving as the campaign's executing.
Hey guys, welcome to Embedded Toolbox, the video interview series where we try to save the world by solving one engineering challenge at a time. And today we're going to be talking about unit testing and trying to make things a little less fuzzy. And the person to help us unfuzz things is Paul Butcher, who's a senior software engineer at AdaCore and lead for the company's HICLASS solutions in the UK. How you doing, Paul?
Hi, Brandon. Yeah, very good. Thank you. How are you doing?
I'm doing very well, thanks. So I just want to sort of set the stage a little bit. In your traditional unit test, are you able to test for, the live dynamic system? What inputs are coming through and how they're going to impact the software that's running? Is that what's typically covered by unit testing, or does it sort of fall short in those areas?
It's it kind of depends on the project you're working on. They're usually, particularly in avionics standards, the first thing you'll need to do is define what you mean by a unit. It often means, a subprogram within some sort of specification, but it can be a bigger thing than that. It could be more of a subsystem. You're tending to test small components of software in isolation, and if you're looking to get more of a realistic, bigger sort of testing infrastructure in place, that's not typically what you would use unit testing for.
So Paul, when you're performing unit testing, how can you be sure that the data that you're using, in your test case is accurate or, at least realistic enough to what your system would experience in the real world if you're, creating the test yourself?
Yeah, it's a great question. And there's techniques to unit testing, things like boundary value analysis, all of the way, usually more often than not, you're going to be manually creating those values. And there is going to be an implicit amount of human bias involved in that. And there's also an inherent problem to do with the number of permutations of data items and the processing capability. Now, it's not feasible to do completeness testing with unit testing in all circumstances. And this is where fuzz testing can step in, because we don't need to go through the process of considering what expected outputs should be for inputs. We can just generate those inputs at a really, really high rate, whilst trying to explore as much of that control flow base as possible.
Can you explain what fuzz testing is and then how it relates to and differs from unit testing?
Yeah, absolutely. Fuzz testing is something that's been around for quite a long time, but it's gaining a lot more popularity in the modern day. And that's mainly due to the increases in hardware performance. So fuzz testing differs to unit testing in that it is an automated input creation capability, if you like. It relies on you providing it with what's often referred to as the starting corpus, so an initial set of test case input data. We're not particularly interested in the expected output, which differs to unit testing. We will take that set of input data and we will pass it to a mutation engine. And the mutation engine will alter those test case files as fast as it can. And they're usually doing it blind, in the sense that they have no understanding of the structure of the data that they're changing. And they will flip bits and bytes at the binary level, send those test cases into the software under test. And as opposed to checking that an expected output matched an actual output, what we're actually doing is we're looking at the behavior of the system. We need some sort of anomaly detection capability to check that it's not fallen over or it's not stuck in a permanent loop. So you can see there that that needs you to mutate the data and fire it into the system and detect for these anomalies at a very, very high rate. And that's where the modern increase in processing time has made this a much more viable solution for application testing.
So I know AdaCore has its GNAT portfolio of tools and that entire offering, but this fuzz testing capability, you have something new there, right? What can you tell us about what you're doing on that front?
Yeah, it is new. It fits in with our dynamic analysis suite. So this is where we have our GNAT test, our unit testing tool, our coverage solution called GNATcoverage, and now we're adding to it a fuzz testing capability called GNATfuzz. We're using as an underlying fuzz testing engine a technology called AFL, which is quite a common open source fuzz testing solution. And we've been supporting that tool for some time, providing compiler expert support and feeding our solutions back up into the public GitHub repository, for example. So we feel that combining coverage, unit testing, and fuzz testing into one suite of tools, the dynamic analysis suite, is a really nice offering. They're all complementary technology for runtime detection of anomalies within your system.
That's great. So I know that you prepared a demo for us today, which is fantastic. I'm excited to jump right in. Do you want to fire up the screen share and show us what you're working with?
Absolutely, yeah. So what we're looking at here is an Ada package specification, and it's trying to show the sort of typical algorithms you'd expect to see in an avionics software system. This particular one is an algorithm that will calculate the speed of sounds through air. So something you typically see in a fast jet. And this is something that I've previously written for aerospace companies when I was a software consultant in a previous life. There's one public subprogram here. It's called getMacValue. And if you feed it sensor data, and more specifically, you give it the air temperature around the vehicle and the speed the vehicle is currently traveling at, it will return the associated Mach value, the number of times the speed of sound has been exceeded. And it's quite a nice configurable algorithm. You can give it the air temperature and the airspeed in a number of different units of measurement, and it will deal with that and perform the necessary conversions. If we have a look at the function itself, we can see that it's going to work out the unit that you've given it, perform the conversions, and down here it's performing the actual speed of sound calculation based on that air temperature. And then it's going to return it to you in a Mach value associated with the speed value that you provided it. One way we can gain assurance that these algorithms are functionally correct would be to use unit testing. That's an approved way of achieving that level of assurance. So we can do that with GNATtest by asking GNATtest to generate a unit test harness for us. For the purposes of this demo, I've already gone through that process. So we can just open the harness project up and have a look at the tests that I've created. So we've got a test for our getMacValue function here. So GNATtest has created the test harness for us and simplified the whole process such that we just need to fill in the body of the harness procedure itself. The particular test I put together is quite simple. There's two loops down here, and they're just taking values from tables, feeding them into the function under test, and then we're going to check that the expected output matches the actual output. And if we have a quick look at these tables, the first one is a correlation of air temperatures in Fahrenheit with the speed of sound in feet per second. And this table down here does the same thing, but the air temperature is in Celsius and centigrade, and the speed of sound is in meters per second. So if we go ahead and execute these tests, which we can simply do by running the test harness, we can see here that they've all passed, which is good. So we've got a pretty good level of assurance now that these algorithms are functionally correct and that our functional requirements have been satisfied. And there's clearly more we could do. We could expand those tables. We could provide more tables that looked at the different units of measurements that we support. But we more than likely still come back with the same result. Those tests, the inputs that we've provided are proving that, giving us assurance that the algorithms are functionally correct. But it's not the full story, because as we've discussed already, it's not telling us about any level of robustness assurance, as in, can the software stand up to inputs that perhaps we wouldn't normally expect to feed it. And this goes back again to the unconscious human bias of creating input data in this form. If this software does indeed have software bugs within it and they can be proven to be exploited, then they become security vulnerabilities. And in the modern age of interconnected systems, this is a huge concern. And fuzz testing is a great way of flushing out any obscure corner case scenarios that can cause your application to crash or to enter an unknown operating state, or indeed enter a permanent loop where you could have a potential denial of service attack. Let's exit the unit test harness project and switch back to the package specification. The first thing that GNATfuzz can tell us is which of the public subprograms within the Ada package specifications are suitable as fuzz test injection points. And the way it does this is by using the Analyse mode. So there's three main operating modes of the tool. You run the Analyse mode to tell you what you can fuzz test. You run the generate mode to generate the harness for a particular subprogram. And then you run the fuzz mode to execute the campaign. So we're demonstrating the tool operating through GNAT Studio here, but what it's actually doing in the background is running the commands. It's a command line driven tool, as all the AdaCore tools are, which makes it easy to incorporate into a tool chain or a DevSecOps pipeline, etc. So if we go ahead and analyze this Ada package, it will immediately tell us, in this window over here that this it's found as fuzzable subprogram, and it's this getMac value function that we've already unit tested, which is great. So we can go ahead and generate the fuzz testing harness by running GNATfuzz generate. If we press execute, it's now creating quite a large amount of code in the background that supports the marshalling of our test case data into binary test case files. We need the inverse mechanism of unmarshalling them back into Ada variables so that we can inject them into the application under test. And then it builds creates a test harness infrastructure that allows us to detect any anomalies in the software as it's executing. The next stage of the tool is to run the fuzz mode. And ordinarily, the first thing that the fuzz mode will do is generate an initial set of values to feed to the mutator. So in this case, it's going to be this sensor data type record. But for the purpose of this demonstration, what we can actually do is go one better, because we can use the data that we already created for our unit test harness, and we can convert that into the binary test case files that our fuzzer needs. So in order to do that, I just need to execute this script, and that's now created our initial starting corpus based on the same data that our unit test campaign was using.
Okay.
In order to execute the fuzzing session, it's just a case of clicking GNATfuzz, start fuzzing session. It's quite a configurable tool. There's a number of different switches and config items that you can pass it at the command line. We'll just stick with the defaults for this demonstration. So if we go ahead and execute and have a look at the messages, we can see here that it's building the runtime. It's going to build the harness, reduce the corpus down. It's going to instrument for the coverage analysis, and then it will run up the nodes on the cores that it found were had the necessary resources available. So the output here is telling us that we've been executing for approximately 27 seconds, including all that build time, and we've already hit 100% statement coverage, which isn't too unsurprising because the starting corpus that we provided it got us most of the way, albeit that we didn't deal with all the units of measurement. So there have been extra paths that the fuzzer has found. And down here, we've got an idea of, well, it shows us our stopping criteria. This is the default one, and whether those rules have been satisfied or not. When they've all been satisfied, the campaign will stop. If we look over here under fuzz crashes, we'll see that actually there's quite a lot of the mutated test cases that the fuzzer has injected into the software under test that have caused the application to crash.
This is awesome.
And it's worth noting here that it's not crashing because it couldn't unmarshal the data because it mutated it in such a way that the data is outside of its ranges, etc. It's crashing because the data was valid, but the Ada runtime environment constraint checking capabilities determined that the instruction calls that you were making were going to invalidate a constraint,
right,
as in range checks failed. Or it could be that we've detected that particular execution caused a core dump file through a segmentation fault, or you could have had that it's just quite a simple check that it's executed for longer than a set amount of time, indicating a potential infinite loop. So if we stop the fuzzing session at this point and have a look at some of these crashes in a little bit more detail. So each one of these entries here represents one of those binary test case files that the fuzzer created that caused the application to perform unusual behavior that we've observed. They're all binary test case files. They're not human readable, but the software will decode them on the fly. So if we move these windows over a bit, we can actually have a look at a human readable representation of that binary test case file and see the values that were passed in that caused this particular, in this case, the Ada runtime to raise this constraint exception. And if we take these values and feed them into the software under test, this get mac value function, we are guaranteed that these tests are repeatable. We will get this crash. And we've made this a little bit simpler within the IDE in that all we actually need to do is double click on the test case and it will rebuild the software in debug mode, put a breakpoint on any exceptions raised, and then it will execute that test, fire in those values and take us to the bit of the calculation that the runtime constraint check failed. And we can have a look at the call stack, and we can use the debugger GDB to analyze these values, work out why this particular algorithm has caused this range check failure. And then we would go ahead and put some defensive coding in around this algorithm. And what we would recommend you then do is you take the data that the fuzzer has found caused the application to crash and add it to your unit test data suite. And this is kind of dynamically building up a regression
Yeah.
test. It's only adding more value to your unit test capability. And remembering that that unit test set is what we then use to create our starting corpus to feed back into the fuzzer. So it's all complementing each other and getting better and better the more we execute it.
Well, that's going to bring us to the end of our time here, Paul, but I do want to give you the opportunity to tell the audience where they should go to find out more about GNATfuzz, fuzz testing capabilities in general. Maybe you have some stuff up on a GitHub. Where should they go to find out more?
The best place to find out about the technology we're working on, we have a landing page on our AdaCore website. You can just Google AdaCore GNATfuzz, GNATfuzz, all one word. And there's quite a lot of information there. I'd highly recommend looking at the AFL GitHub page. There's a very strong community there. There's people there that will tell you about the various groups. But if you're interested in building your own fuzzer, that they can help you do that.
That's great. Well, thank you so much for your time. And I'm really actually looking forward, Paul, to getting you back on and going through some more specific use cases and test cases, I'm sorry. And then also maybe we'll be dealing with some of the AI and ML at some point here in one of these.
Absolutely. That would be great. Yeah.